All right, we'll get started. Sorry for my delay. So the plan is to cover two more topics from this Bayesian linear regression. In particular, if you remember what we did before, last time we talked about how to write out the model using the normal model as the basic, but then we're adding a continuous predictor. And then we talked about how to think about priors for the three different parameters. So we have an intercept, beta 0, we have a slope, beta 1, and then we also have the sigma from the normal model. So that's why we have three parameters. We did them weakly informative priors for posterior inference, and then we also introduced how to write jet code for doing that estimation. Okay, so that was a recap of what we did. So today I want to spend some time first on certain things that we can do once we get the model estimation done. For example, we can do predictions for simple linear regression and stuff like that. So we're going to talk about that first, and then I'll introduce two other ways to give priors in this kind of context that can give us more flexibility. So one thing that we could do for Bayesian inferences, once we get a model fit, is if you remember, we have this equation 16 as our basic model setup. We're assuming that the expectation of the outcome variable y is a linear combination with the intercept beta 0 plus beta 1 times the predictor variable x. If you remember and imagine how Bayesian inference can be done after we do the MCMC estimation, we have a lot of draws, right, of beta 0 and beta 1 and sigma, right? If I run my MCMC for like 5,000 iterations, which is what we usually do with JAGs, if you remember, then technically we're able to get 5 pairs of beta 0 and beta 1. And then, of course, another 5,000 draws of sigma if we want to use them for later investigation and all that. So one thing you could compare to what you do in a frequentist framework. In a frequentist framework, you just run the LM functions in R, right? And they're going to give you the point estimate for beta 0, beta 1, and they also give you a 95% confidence interval or like the standard error and all that. However, in Bayesian framework, we get posterior draws for all of the parameters of interest. So just imagine that after we have done our MCMC estimation, we have a bunch of draws of beta 0 and beta 1, and then each of them actually going to correspond a line in the space. Okay, so technically, however many pairs of beta 0 and beta 1 you're going to have, you could however many straight lines going through the data cloud. Okay, so imagine how that is different from the frequentist point of view. So one thing, of course, is, well, I have a bunch of beta 0, a bunch of beta 1. I don't know which one is the best to use. So how about I take the mean? I take the mean of each. I get beta 0 tilde. So I use this tilde notation to represent the mean of all of the beta 0 draws. Beta 1 tilde is the mean as well. So then I can kind of find, quote, best line of fit using the posterior mean. And then I can graph that out if that's what you're interested in. Okay, so equation 17 shows us one way to figure out that straight line. And then in addition to the best straight line itself, we're always curious about the uncertainty of the line estimate. Like I said, the posterior estimation of our model gives us a large number of draws of beta 0 and beta 1. Okay, and then themselves are actually giving us uncertainty quantification of the beta 0 and beta 1s themselves. So we should try to utilize that when we're trying to learn about the particular regression model that we're fitting. Okay. So I'll show you some code and then also some graphics to see how things can be done. So we talked about, well, for point estimate, I can get the posterior mean, then I'm done. I get one best line. But if I want to learn the uncertainty of the line estimate, we can draw a sample of, I'm just using capital J whatever number is, as long as it's smaller than the number of posterior draws you have. We can actually get a sample of J rows from the matrix of the posterior draws and collect all of the line estimates. Okay, so I'm using, so posterior underscore new, that is the object, I think, where we save the posteriors, and then I'm just trying to get the means and also later on doing the plot. Okay, so I just want to show you a couple of things over here. Okay. So the data cloud doesn't change because all of the dots are just what the data tells us. Okay, but you can see that we have 10 different straight lines, okay, going through the data cloud. So this is what I was trying to say that, well, if we have a large number of posterior draws of beta 0 and beta 1, let's just say it's 5,000 in our scenario. I think in our estimation, that's what we did. So technically, I can have 5 different lines going through the data plot, okay? Because each pair of the posterior draw corresponds to a straight line. So of course, that will be too much to plot, or we won't be able to see anything. I guess everything will just be a black area over here. So I'm picking the first 10. So the code over here, as you can see, is trying to only get from the post. And that's the matrix of all of the posterior draws. I'm only getting the first 10 rows. Okay. And with that 10 rows, I'm able to see going through the data cloud and only 10 different straight lines over here. I know it's hard to count and all that, but trust me, because of the code that we write in this way, we are looking at 10 different straight lines going through it. Okay? All of them is a possible regression line, right? Because each of them represents a row of your posterior matrix. But I just want to show you how this is, this can be done as well, how this compares to a frequentist estimation if LM function is what you have been doing in the past. Okay? So that's one thing. So we call this simulate fits from the regression model just because each pair of the beta 0, beta 1 gives us one line fit, and you can get multiple if you want. Another type of Bayesian inference is, of course, trying to learn about the outcome variable, because at the end of the day, the regression analysis that you can do, regardless of whether you're doing Bayesian method or frequentist method, is you can learn something about the mean of the outcome. So what if one wants to learn about the expected log expenditure of ACU? So that's the outcome variable, yi, for a specific log income value. So that will be the xi value. So the question here is, well, if I know a consumer unit's log income value, that's their xi, I wanted to know the expected outcome of their yi. Okay, so what does the model tell us after we fit the model? So one thing we could do, so first of all, this is always the relationship, right? After we, well, before, that's just what the model is saying. The expectation of the outcome is a linear combination of the intercept and the slope multiplies with the predictor variable. So we have, once again, posterior draws for this beta 0 and beta 1, just like the previous step that we got. So one thing we could do is we can get a simulate sample of the posterior of beta 0 plus beta 1x by computing the sum of them. So we get the draws of beta 0 and beta 1, and x is given to us. If we're interested about a particular observation, then we should be able to actually generate a large number of expectation of y as well. Okay, so x is fixed for a particular consumer unit. Each pair of beta 0 and beta 1 is going to give me one expectation of y. Okay, and I can do this for a large number of times given a particular x. So the code over here, which I would imagine some of you might want to use that for your project later as well, if this is relevant. So here you can see that we're writing a function, and we call it like just trying to compute the expected outcome for one observation. So what we're getting, as you can see, is that we're getting from the post, which is the matrix of saving all of the parameters. I'm extracting the beta 0, I'm extracting the beta 1, and I'm extracting beta 1 multiplies with x. So x will be whatever the predictor value that I'm looking at. And then by doing this, I will be able to, extract all of the values that I want for this expectation of y. Okay. So for this function, I'm applying it with x equals to 1, equals to 5, equals to 7, equals to 9. That's the log income of this 5 or 4 different possible predictor values, and then we can then graph it on same graph. So let's take a look at what we gonna have, and then give you a chance to read the graph a little bit and talk to your neighbors about it as well. So like I said, we're looking at 4 different values of x. So we have x equals to 1 in the first panel, x equals to 5, 7, and 9. Okay. So the graph might be a little bit unusual than what we usually see. And then you see that for each panel, let's just say for x equals to 1, that is log income equals to 1, we have a posterior distribution of our expected y. Okay. When we get to x equals to 5, we get this, well, x equals to 7, and x equals to 9. Okay. So maybe spend a moment, and for remote students, this is slide 36. of the slides that we posted. I want you to take a moment to look at maybe talking about how the mean changes, okay? As you can see, the 4 different histograms, or just the density plots over here, as well as their variance. Because there's a clear trend, I think, as we're looking at this combination of different X, and then we have simulated a large number of expected outcomes for given those X values, given our beta 0, beta 1. And then we're seeing this 4 different density plots lining up in a particular way. So take a moment and then try to think through what we're plotting exactly. Why do we see what we see over here, and whether it makes sense to you. So let's take a moment. So this is slide 36. All right, any thoughts? Like I said, each panel represents a particular X value. Okay? And then this kind of plotting technique is trying to put all of the density plots on one plot, so you can still share the same x-axis. Okay, so the x-axis, the expectation of the y, which will be the expected log expenditure. And then each panel shows you, I guess, on the x-axis, you would know what the value of the expectation value is. And then each density plot shows you, a different center and different spread. I guess the most obvious general trend, I would say, is as X increases, say from 1 to 5 to 7 to 9, right? We're seeing the increase of the expected outcome as well. Because if you can see here, this is, I don't know the value exactly, but close to 5 at the mean roughly. And then we get something close to 6.5, right? For X equals to 5. And then a little bit more than 7 for log X equals to 7, and a little bit more than 8 for log of income equals to 9. Okay, so that probably tells us that beta 0 or beta 1, the slope itself is positive, okay, because you're having this positive effect going on over there. Okay. Any other comments or questions of what we're seeing? Any guesses of why? So another feature I would say, if we look at the 4 density plots together, is that as the X increases from 1 to 5 to 7 to 9, not only the mean, right, is shifting to the right, like increasing gradually, but also the spread of each of the density plots seems to be smaller. Okay, it's getting smaller. And we know that smaller spread translates to less uncertainty, right? We are more confident about the expectation value, for example, for X equals to 9, X equals to 9, we know that the mean is roughly a little bit more than 8, and we get most of the draws around that very small interval. Okay, that's what this density plot is showing. But then if we look at log income, which is X equals to 1, yes, it is small at the mean, which is we're close to 5, but also it seems that we are not very confident, or the posterior distribution is showing a large variability, okay? Meaning that it's a higher level of uncertainty of what we think this expectation value would be. So I will point that out first, and maybe at the end, we can come back to see why that is the case. Okay? But if anybody has anything to comment on, so maybe let me go back to the previous slide a little bit. So of course, if you want to see how the code can be done, you can check out this example. And then this is roughly how the original data looks like. So one thing I guess we could probably pay attention to over here is that if you look at the dot plot, like the scatter plot over here, ignore the straight lines. Those are the simulated fits. Just look at the dots themselves. One thing you probably will see that, well, the majority of the plot or majority of the dots are between 9 and 12 over here. Okay. And that's the X, right? If we think about the log income, okay, that's the X. So remember the 4 examples I gave? I gave X equals to 1 or 3 or 5 or 9, right? That's what I did, or 7 or 9 or something like that earlier. So you will see that, well, only the last one is kind of in the main chunk of what the data cloud is showing. Okay, so we have a lot more data around X equals to 9, whereas we have very few data points, right, for X equals to 1 or 3 or 5. So as we know, the more data that you have, the more information that you're going to have for that area of your X as well. So that, not surprisingly, translates into the plot that we saw earlier, that only when we are looking at, okay, so I did 1579, I guess. So when we are in the area where we have a lot of data, x equals to 9, if you remember that that scatter plot. So we are having a much more confident or much more concentrated posterior expectation. Okay, so that's the main reason of why you're seeing it to be shrinking as we go along for the x value. So all of this, like I said, comes back hopefully to you as at the very beginning of the semester, we talked about that the main the posterior is a combination of the data and the prior. The more data that you have, the larger the influence of your data in your posterior are going to be. So this is also showing it up in a particular model for different pockets of data. So that's the expected outcome. That will be expected of the expectation of y. And then I'm looking at another set of example as well. So if you can see here, I'm looking at 10, 11, 12, and 13. And if we still remember, so first of all, it's still increasing, right? The mean is increasing. And then now the spread is going the other direction, okay? It's going wider and wider. And if I once again come back to my scatter plot, okay? So this is looking at from 10 to 13, right? Whatever 13 over here. So you can see that as we move along, the amount of data, right, move along x from smaller to larger, from 10 to 13, you can see that we're getting less and less data as x increases in this range. And that's once again why we're seeing a higher level of uncertainty for the predicted, I should say, for the expected value as well. Okay, yeah, so get the intuition. And of course, if you want to do this kind of posterior summary for your projects, there's our example code that you can use, and then you can always update it to your own use. And then, of course, if I want to look at specific ones, I can just do some kind of summary, right? If I get the values, what I calculated before, and then I get the quantiles, this is exactly trying to get the 95, in this case, 95% credible interval for the expected value. And then we can do a table, and then, of course, do the interpretation accordingly. Okay, so the plot is one way to summarize, and then this kind of table is another way to summarize. Okay, so totally up to you what kind of things you want to use, and just make sure that the interpretation is correct, because we're talking about posterior probability of a 90%. Yeah, 90%. Sorry, yeah, this is a 90% posterior probability credible interval. So with that, we should be ready to talk about how to make a prediction. Okay, so we talked about how to get the expected value of y from our beta 0, beta 1, and all that. And a natural thing to do, which is what we have been doing in the past as well for those simpler models, is how to make prediction of future responses. Mathematically, the model is equation 19, okay? As we know that, well, if I know my xi for a unknown with new observation, that's the log income value for this consumer unit. If I get beta 0, beta 1, and sigma, those are my posterior draws, right, of my parameters in the model, then I should be able to, right, sample a new yi, which is the predicted value from this normal distribution. So you can use R norm actually in that kind of exercise. Okay. So of course there is variability because beta 0 and beta 1 is what we talked about before. We have a large number of draws of them out of our MCMC estimation. So we don't just get 1 point for each of them unless you just take the mean. Otherwise, each pair of beta 0, beta 1 going to give you, right, different means. So that will translate also, I think, into the variability overall in the yi predicted in the future as well. Okay. So what I'm trying to say is, not only this part has some variability because of the MCMC estimation, we have large number of draws of beta 0 and beta 1, but also once we do another R norm, we're introducing variability in the outcome as well. Okay, so once we're looking at the two sources of variability in the outcome, you will see that we're going to have two contributing together. One is about the parameters themselves because of the Bayesian inference process. And then the other is, well, we are going to do an R norm based on equation 19 to make a new prediction for a yi. So that's the basic, okay? And then of course, in practice, when we do this kind of simulation, just like what we did in the past, we can write a big loop, Okay, we can do, for a first pair of my beta 0 and beta 1, let me first calculate my expectation of y, and then I can sample that from my normal data model. And don't forget, there are 3 parameters in the model, beta 0, beta 1, and also sigma. And sigma will come into play in your estimation, in your prediction as well, because you need to follow this equation 19, which is a normal model for your y. So to sum up, what we did earlier is only looking at the mean part, okay? And the mean part has only beta 0 and beta 1, so you only use the pair beta 0 and beta 1 when you're trying to only come up with the mean. Okay? But because you have a large number of draws of the pairs of beta 0 and beta 1, you have some variability over there. That's what the plot that we're doing earlier, okay? And now when you're doing prediction, you have one extra layer of variability, because equation 19 requires you to sample a normal outcome with the mean beta 0 plus beta 1 times xi, and also the sigma that is estimated from the model. Right? So there are 2 sources of variability, and then in terms of coding, you get beta 0 and beta 1 over here, and then don't forget you have your sigma, which should come from the same iteration of your draw. So this is the procedure. And of course, I think we always try to cover how to do it in R. So once again, we wrote a function over here. Instead of 1 expected, we call it 1 predicted. So what we're doing over here is that given a particular S value, I want to see how I can predict a new Y for this observation. So first of all, I'm going to get the mean. Okay, so this is the same as before, right? I'm getting my beta 0 plus my beta 1 times X. And then the second step is I need to do another R norm step that I was talking about, the previous equation. So you can determine how many you want to draw, of course, the mean, and also the sigma from the same iteration. And then, of course, you can summarize, put it into a data frame and then trying to report it. So once again, I do 1579 just to get us started. So we're going to do this mapping as well to get that graph. Okay. So this is what we're getting. Okay, so sorry about this. I think this should be log. Yeah. So here I have my x equals to 1 equals to 5, 7, and 9. Okay. And then nowadays here is not the expected log expenditure anymore. It's going to be the predicted. So we can use y tilde to represent it. Okay. Overall, we see an increasing trend, right, in the mean. Okay. And overall, I think that the spread doesn't seem as different as compared to before. Okay. And that is also because we have the other source of variability when we're taking the random draw of the normals in the process. Okay. But I should also say, even though they don't look quite different in terms of the spread, but each of the density over here is having a larger spread than the mean earlier. Okay, so if you kind of remember this plot, and let me go back to the mean example earlier here. So this is the expected y, okay? And you can see that, well, the spread seems much smaller compared to before. They're different, first of all, but also overall, the scale is smaller than the predicted version. And I just want to say that the spread, given what we talked about so far, has 2 contributions. One is the expected, and the other one is the sampling itself. So that's why, because of the extra layer of variability in the sampling process, we're seeing a larger spread in the prediction compared to only the expected. So everything hopefully makes sense. I mean, the more that you see it and synthesize it into what we have learned before, this hopefully starts to make more sense. And then, of course, you can also return tables, so you get the exact numbers, and then you should be able to talk about the outcome. So another way to look at why the prediction will have a larger variability is that earlier, for log income of $5 for a consumer unit, a 90% probability, posterior probability, or 90% credit interval for the expected log income is 625 to 662. But if I'm doing one step further to do the prediction, okay, and then the prediction actually going to have a 90% interval of 524 to 761. Okay, so if you compare this to this one and this one, so clearly the prediction is wider. Okay, the prediction interval is wider, and like I said, it is because not only we have the variability of the beta ones and beta zeros in the mean. But in addition, in the prediction, we also have a layer of that sigma in our sampling model for the normal. So that's why, not surprisingly, you're getting a wider interval. Okay, so this is will be true in other contexts as well. But I just want to show you that, well, given what we have talked about in the past, this hopefully makes sense, as well as also for your project or other applications, you can consider using this kind of technique to show your results and all. Okay, okay, yeah, so the main thing, like I said, is that for our parameters, beta 0, beta 1, and sigma, because of the Bayesian inference that we're doing, you have a large number of them out of your MCMC estimation. Okay, so because of that, the uncertainty in the parameter estimation translates into the uncertainty of your expected outcome, right? That's why we have those density plots, and it also translates into the prediction outcome as well for those variabilities. So we can see that the prediction will have a higher level of variability because we also need to do the random sampling process of that R1. Right, so